In this video, we're going to talk about the electrophilic attack on conjugated dienes, also known as a 1,4 addition. So this is a reaction that we've previously seen back in CHEM 1. We saw what happens when you take a double bond and react it with a halogen acid. You end up doing a Markovnikov addition where the halogen ends up on the more substituted carbon and the hydrogen ends up on the less substituted carbon. This ends up being a little trickier when you have a conjugated system. So that would be called a 1,2 addition. So the 1,2 comes from the numbering of the molecule and just indicating that the two pieces of the molecule that were added next to each other. So on neighboring carbons, 1, 2. And the other double bond was unchanged. So this is our 1,2 addition. This is the normal Markovnikov addition. The other product came from what's called a 1,4 addition. So notice that the two pieces of the molecule that were added ended up 4 carbons away. So this is a 1,4 addition. Now the breakdown of these products, this is going to be 78% of the products, and the 1,4 addition is going to be 22%. So before we talk about, how to favor one over the other, let's look at how this actually happened. So in order for this reaction to occur, we actually have to go through a common intermediate. So we're going to look at the mechanism just like it was a normal Markovnikov addition. So let's take our alkene and we're going to go ahead and protonate it because that is our first step. All right, so we are an acid, we're going to protonate something, we're going to protonate that double bond. So when we protonate the double bond, the hydrogen goes on the less substituted carbon so that we can form the more substituted carbocation, which brings us to a crossroads here. So if the chlorine just comes along and attacks the carbocation, we'll call that route A. What we end up with is our normal Markovnikov addition product, right? The 1,2 addition. But if instead we go through a resonance form by taking the pi electrons and moving them here, we end up with a new carbocation, which, yes, is primary, but remember also it's allyl. So this is as good as a secondary carbocation. Not as good as a secondary allyl carbocation, but still pretty good. So then the chloride can attack that carbocation. We'll call this route B. And we end up with our 1,4 addition. So there are a couple things here to consider. Other than the fact that we've created a perfectly reasonable allyl carbocation, we've also created the product that has the more substituted alkene, which is a point in its favor. And that's actually one of the things that contributes to the formation of the 1,4 addition product. So let's look at how we can actually get one or the other. So note that if we did this at room temperature, we would end up with mostly the 1,2 addition product. So if you end up with the 1,2 product, this is kinetic control of the reaction. This is going to predominate at low temperature. So if you do room temperature or lower, you're going to get the 1,2 addition product. And that's because this is the fastest forming product. It forms from the carbocation that is immediately made. right? It's a secondary allyl carbocation. That's pretty good. It doesn't necessarily need to rearrange. But you also could potentially end up with the less substituted alkene, depending on what your substrate looks like. So this isn't going to happen every time that your alkene ends up less substituted, but it is a possibility. If you end up with the 1,4 product, this is going through thermodynamic control, which is going to predominate at high temperature because you're going to give the system the energy required to go through that carbocation rearrangement. And you're going to end up with the more stable product. So you will probably end up with the more substituted alkene. And again, this is going to predominate at high temperature. So if you see something like 50 degrees C or higher, anything really that's indicating higher than room temperature, you're probably going to be favoring the 1,4 addition. So that's the difference that you want to be looking for. Your reaction conditions for 1,2, you're going to have a halogen acid of some sort, and it's 25 degrees or less. For thermodynamic control, I would say greater than 40 degrees typically. So before we move on to our next type of reaction, the Diels-Alder reaction, we're going to discuss kind of a broader area of reactions real fast. So this is the pericyclic reaction. A pericyclic reaction is one that occurs through a single cyclic transition state. So this reaction is a photochemical reaction, meaning light is going to trigger it. And it's going to happen just by these pi electrons attacking this carbon, these pi electrons attacking this carbon. So you're going to end up with a cyclic transition state. This reaction is kind of happening all at once. And this is actually also how our body takes cholesterol, or a form of cholesterol, and turns it into vitamin D. So that's why when you go out into the sun, it actually gives you the amount of vitamin D that you need, and why it's important to go outside, and why people who live in areas that actually go through periods of darkness during the winter need to be exposed to light, is because our bodies produce the amount of vitamin D that we need if we just spend a couple minutes in the sun every day. And that's actually just a photochemical reaction.